Welcome back to part 4 of our Unity interview question answer series, where we will be covering over 100 plus real interview questions across multiple parts. This series covers interview questions ranging from beginner to advanced level. If you missed previous part, make sure to check it out first, then let's jump right in. And hey, if I miss any question that you have faced in interview or think should be included in this video, let me know in the comments. I would love to add in the future video. This is part 4, let's get into it. What is the difference between material and shared material in Unity's MeshRenderer? In Unity, the MeshRenderer uses material to define how an object looks. But there is a key difference between material and shared material. When you use renderer.material, Unity creates a new instance of material just for that object. If you change its color or texture, only that game object is affected. Others stays same. But with the renderer.sharedMaterial, you are modifying the original material asset. That means every game object using that material updates instantly. Let's understand the difference with the example. Suppose you have two cubes and you have assigned the material name red material, which has a red color, to the mesh render of the both cubes. Now we attach this cube to one of the cubes. In this cube, we have changed the color of material and shared material's color property. If we run this by setting the use shared material to false in the inspector, only the cube with the script will return to blue. The other cube stays red. A new material instance was created for this cube. If we run this by setting use shared material to true in the inspector, both the cube turn to green. The shared material was modified. So remember, use material for object-specific changes at the runtime. Use shared material when you want to global changes to all the objects sharing that material. Let's move to the next question. What is the difference between shader and material in Unity? In Unity, shader and material work together, but they are not the same thing. A shader is a small program that runs on the GPU. It defines how an object should be rendered, things like lighting, transparency, color, blending, and special effect. Think of it as the blueprint for rendering. A material, on the other hand, is an asset that uses a shader and lets you customize its properties. For example, you can assign a texture, pick colors, or pick the numeric values like smoothness or metallic values. So, you write or choose shader once, then you create multiple materials from it, each with the different settings. That's how you can make two objects use the same shader but look completely different. In short, shaders are for the rendering logic and material are uses for the customized look based on that logic. Let's move to the next question. How can you play an audio clip in Unity? To play an audio clip in Unity, you typically use the audio source component along with an audio clip. First, select your game object, add an audio source component. Then assign your audio clip in audio clip field. Audio clip could be .wav, .mp3 or .ogg file. If you want it to play automatically when the game starts, check on the play on awake box. You can also trigger the audio through code. Here we have used audiosource.play. It will play the assigned clip. Also, there is a audiosource.play one stop clip that will play a clip once without interrupting others. You can stop the audio using the audiosource.stop method and set the audiosource.loop to true to play the audio clip in loop. So, whether it's background music, sound effect, or voice lines, Audios is your go-to-go tool to audio playback in Unity. Let's move to the next question. Explain Unity's primary light types. In Unity, lights are used to illuminate the scene and affect how objects appear. Unity offers 4 primary types of light source: directional, point, spot, and area. Each type has a distinct characteristic suited for a different light effect. First is directional light. The purpose of directional light to simulate a distant large source such as the moon or sun that is infinitely far away. The light's position does not matter, but its rotation determines the angle at which light rays strikes the object. Every reality scene automatically includes a directional light. Next is point light. A point light is located at the single point in space and casts light all directions equally, like a light bulb or candle. Point light intensity decreases with the distance. The position of the light source determines where the light is emitted, and the range property controls how far the light reaches. Great for simulating local light sources like lamp, torches, or explosion. Another light type is spotlight. A spotlight emits a light from a single point within a cone-shaped region. Like a point light, it has a specified location and range, but the light is constrained to a defined angle. The spot angle property controls the width of the cone, while the light intensity follows the edges. Spotlight is useful for flashlight, car headlight, and stage lights. Next is area light. An area light emits the light from a defined surface, such as a vehicle, which is creates soft and subtle lighting. Area light simulates a large light source like window. Area light cannot be used in real time. It is only for a backed pre-computed lighting. Each of these lights can completely change the atmosphere of your scene, from harsh sunlight to cozy indoor vibe. And don't forget, Unity also support ambient lighting and emissive materials for subtle global illumination. Let's move to the next question. What is terrain in Unity and how is it used? In Unity, a terrain is a spatial game object that lets you create a large natural landscape like mountains, valley, and open fields. It's perfect for open world and 3D adventure game. To add a terrain, just right-click in the hierarchy, choose 3D object and terrain. Unity will generate a large flat surface that you can start shaping right away. From the terrain inspector, you can sculpt the surface, raising or lowering the ground from the hills, cliff, or the plains. You can also paint texture, add trees, grass, and rocks to make your world more realistic. Terrains are highly optimized for large environments and can even connect it to neighbor terrains for expanding your world seamlessly. In short, Unity's terrain system is your canvas for building vast, detailed, and immersive landscape for your games. Let's move to the next question. Comparison between IR to CPP and Mono builds. In Unity, your project can be built using two main scripting backends, Mono and IR to CPP. Both compile your C# script, but they work differently. Mono use just-in-time compilation or JIT, meaning your code is compiled while the game is running on the user's device. This makes build time faster during development, which is great for testing and iteration. IR to CPP, on the other hand, uses the ahead of time compilation or AOT. First, it converts your C# code into C++, then compiles that C++ code into native machine code before the game runs. This makes IR to CPP builds slower to compile, but they run faster and more efficiently. Mono builds are great for development and quick testing, while IR to CPP builds are ideal for final release, especially on the platforms like Android, iOS, and console, where performance and compatibility matter. In short, Mono is for speedy development and IR to CPP for high performance and platform support. Let's move to the next question. Explain two target architecture, ARMv7 and ARMv64, in the context of building Android. When building for Android in Unity, you will often see two target architecture, ARMv7 and ARMv64. These refer to the different CPU architecture that determines which device your game can run on. ARMv7 is 32-bit architecture, most usually in older or lower-end devices, released before 2015. It's limited to the 4 GB of RAM and generally slower. ARM64, on the other hand, is a 64-bit architecture. It supports larger memory, better performance, and enhanced security. This is standard for modern Android devices. When a player downloads your game, Google Play automatically serves the correct version. ARMv7 for older devices, ARM64 for modern ones. And here's an important note. Since August 2019, Google Play requires all apps to include 64-bit version. So, when building for Android, always check both ARM7 and ARM64 if you want to game to support wide range of devices. Let's move to the next question. Describe Unity's asset bundle system. An asset bundle is essentially a compressed file containing one or more Unity assets. This can be anything from texture and 3D models to audio file and prefabs. By packaging these assets into a bundle, you can load them dynamically during gameplay, instead of bundling everything directly into the game executable. There are a few key benefits of using asset bundle. With the help of asset bundle, you can reduce initial download size. By separating assets into bundles, the core application can be smaller, leading to a faster download and installation for user. You can push out a new content or patch without needing a full app update. Asset bundle will also help you for better memory management. You can load assets only when required and unload them when you are done. Creating asset bundle in Unity is simple. First, you mark the asset in the editor for bundling using the inspector. Then, you build the bundle using the build pipeline.buildAssetBundle method. This creates a separate asset bundle file ready to distribute. Now, how do you use this bundle? To load an asset bundle at the runtime, you use the asset bundle class. And when you are done, unload it to free up memory. Unity also supports a platform-specific bundle, so you can create a different version of the same asset for different devices, whether you are targeting Android, iOS, or PC. Unity can optimize asset for each platform. Additionally, asset bundle can be compressed. You can choose from a compression method like LZ4 for faster compression or LZMA for higher compression ratios. Asset bundle can have dependencies. Some bundle might need to another to function. Unity automatically handles this. So when you load one bundle, any required dependencies are loaded too. There is also manifest file. Help you to manage everything. Keep tracking of what's in bundle and its dependencies. One of the coolest thing about asset bundle is how easy they are to host and update. You can store them on server or in cloud storage and load them dynamically. This makes updating your game seamlessly. You can roll out new levels, skin or assets without forcing a player to download a full update. 2. Get most out of the asset bundle. Remember, keep bundles small. This reduces loading time and keeps everything organized. Load assets asynchronously. This helps you to prevent frame drop and keep your game smooth. Test load time. Make sure the asset loads quickly, especially on mobile devices. That's it. If you are working on a large project or just starting out, you might want to be consider Unity's addressable asset system. It's newer, more robust solution that build on asset bundle, offering better management and easier to integration with cloud services. But for many projects, asset bundle are still reliable way to handle your game assets. Whether you are reducing your app size, updating content, or improving performance, asset bundle have got you covered. Let's move to the next question. What is the purpose of using Unity's physics material component? In Unity, physics material control how object reacts when they collide, whether to slide, stop, or bounce. They are essential for creating the realistic physics behavior in your games. You can create a physics material by right-clicking in the asset folder. Select Create, then select Physics Material 3D or Physics Material 2D, then naming it anything you like. Each physics material has 5 main properties that define its behavior. The first is dynamic friction. A low value like 0.1 makes objects slide easily, and high value like 1 makes them stop quickly. As an example, imagine a box on ice. If its dynamic friction is low, 0.1, it keeps sliding, but if it's on a rough ground with the high value 1, it stops fast. Next one is static friction. This controls how much force is needed to start moving an object from a rest. If static friction is high, object won't move easily, and if static friction is low, even a small push make them slide. Think of a heavy crate. If static friction is set to 0.8, it takes more force to push, and if it's set to 0.1, even a slight push make it move. Another property is bounciness. It defines how much an object bounces after hitting the surface. 0 means no bounce and 1 means full bounce. A basketball should have 0.8 bounciness, while a bowling ball should have 0. We also have a friction combined mode. Determine how friction works when two objects collide. It has 4 options: average, minimum, maximum, and multiply. Average takes the average of both object friction. Minimum uses the lowest friction value, while the maximum uses the highest friction value. Multiply both the friction values for unique effect. If a metal ball with the 0.2 friction rolls on the rough ground with the friction 1, if set to minimum, ball slides more. If set to maximum, ball slows down fast. Same as friction combined mode, we have a bounce combined mode, but for bounciness. It also has a average, minimum, maximum, and multiply options. If a rubber ball with the bounciness 1 falls on the ground, which has bounciness 0.2. If set to minimum, the rubber ball has a low bounce. If set to maximum, the ball has a full bounce back. Now that we know how physics material works, let's see some cool use cases. In racing game, use low friction for slippy icy road. In sport games, add a high bounciness to a basketball. In a platformer, use high friction on walls to prevent sliding. With a few adjustments to a physics material, you can make your game world feel more realistic, responsive, and dynamic. Let's move to the next question. What is monobehaviour in Unity? In Unity, almost every script that you write inherits from a special class called monobehaviour. This class is the core bridge between your C# code and the Unity engine. It's what lets your script actually interact with the game object, handle input, move characters, detect collision, and so much more. Without inheriting from monobehaviour, your script is a just plain C# file. Unity won't recognize it and you can't attach it to any object. When your script is inherited from monobehaviour, you unlock the access of Unity's lifecycle methods. special function that runs automatically at different points during the game. Here are the most common ones. Awake runs when the object is first created. Start runs once when the game begins. Update runs every frame, perfect for movement and input handling. FixedUpdate runs at the fixed interval, mainly for physics calculation. OnDestroys called when the object is destroyed or scene end. Here is a simple example of monobehaviour. Because this class inherits from monobehaviour, it can be attached to a game object in the Unity editor. When the game starts, the start method runs once and update runs every frame, giving your life to your player. So in short, monobehaviour is a foundation of almost everything you code in the Unity. It connects your logic to Unity's engine system, physics, rendering, input and more. Mastering monobehaviour means mastering how your script truly behaves inside Unity. Let's move to the next question. Explain script execution order in Unity. In Unity, every script follows a specific execution lifecycle, sequence of events that define when your code runs and how your game object behaves. Understanding this order is key to writing clean code and predictable game logic. Unity's lifecycle can be broken into 5 main phases: initialization, gameplay, physics, rendering, deactivation, and destruction. Let's go through them one by one. When a scene starts or an object becomes active, Unity runs initialization method. When a scene starts or a game object becomes active, Unity first calls awake. This runs once when the script is loaded, perfect for initializing variable or loading data. It's even run if the script is disabled. Next is OnEnable. It's called every time the object becomes enabled and active in the scene. It always calls after awake on the same object before any start call. This is useful for subscribing to events and resetting the object state when reacting. Start function called once before the first frame update. Only the script instance is enabled. It is used for initialization that depends on the other object being initialized or for setting up the initial game state. Once the initialization is done, Unity enters the update loop, which repeats every phase. Think of it as a heartbeat of your game. First comes the FixedUpdate. It runs at the fixed time interval. This is where you handle physics and consist time-based action. Update call once per frame. Update is a primary function for general game logic, input handling, and non-physics related update. Then comes the LateUpdate, which runs after all update calls. It is used for camera movement and or other action that need to be happen after all update calls have completed, ensuring they react to the final state of the object. After all logic and physics update, Unity renders the scene. This phase involves several special callbacks. As we wrap up things, we focus on cleaning up with the help of onDisable and onDestroy function. OnDisable call when the object becomes disabled or inactive. OnDisable is a counterpart of OnEnable, used for unsubscribing for events or cleaning up the resource when the object is temporarily deactivated. And OnDestroy is called when the game object or script is destroyed. This is the final cleanup phase, used for releasing resources and performing any last-minute task before the game object is permanently removed. This Unity script lifecycle is like a carefully arranged sequence, from setup to execution to cleanup. By mastering when each function runs, you can write scripts that behave smoothly, efficiently, and predictably across all stages of your game. Let's move to the next question. Explain the difference between update, FixedUpdate, and LateUpdate in Unity. In Unity, the three special methods, update, FixedUpdate, and LateUpdate, control when and how your code runs in the game loop. Understanding how they differ is one of the most important skills for smooth, responsive, and predictable gameplay. Let's start with the update. Update is called once per frame. That means the faster your game runs, the more often it's called. It's perfect for logic that needs to run every frame, like reading player input, handling non-physics movement, or updating UI elements. When weak object is in update, remember to multiply by Time.Deltatime. This ensures a consistent movement speed across different frame rates, so your game feels smooth no matter how powerful the device. Next up is FixedUpdate. Unlike update, FixedUpdate is called at the fixed time interval, independent of the frame rate. By default, Unity calls it every 0.02 second or 50 times per second. This is the place for anything physics related, applying force, adding torque, or moving rigid bodies. Because FixedUpdate runs in sync with the Unity's physics engine, it ensures consistent, stable behavior even when the frame rate changes. In short, if it is moves because of physics, it belongs in FixedUpdate. And finally, LateUpdate. LateUpdate is called once per frame, but it runs after all update methods have finished for every game object.
That makes it ideal for things that depend on the final state of object, like having the camera follow the player after they have already moved. By running last, LateUpdate ensures everything is in the final position for the frame, preventing those little visual glitches or camera jitter. So here is the quick rule of thumb. Use update for input and frame-based logic. Use FixedUpdate for physics and rigid body movement. Use LateUpdate for camera adjustment or anything that depends on other updates. Mastering when to use each of one give you full control how your game feels and perform, making your gameplay smooth, stable and professional. Let's move to the next question. What is the difference between having one update and having 1000 update methods in Unity? In Unity, every active script that has an update function gets called once per frame by the engine. That means if you have just one update, Unity also need to make one call every frame. But if you have 1000 update method across different scripts, Unity has to call each one of them every single frame. That might not sound like much, but it adds up. Each update call has a small bit of overhead. So, having 1000 separate updates means Unity spends extra time just managing and call those updates, which can hurt performance especially on mobile devices or larger projects. A better approach is centralize your updates. Instead of giving every object its own update method, you can use one manager script that keeps list of objects and update them in single loop. You can also use coroutine, events or invoke repeating for these things that don't need to update every frame. So, in short, one update is usually more efficient than 1000. Unity can handle both, but minimizing the number of update calls lead to cleaner, faster and more scalable code. Let's move to the next question. Awake and OnEnable order for two objects in Unity. Let's see what happens when two objects, test1 and test2, both have this simple script. Now, in Unity's execution order, awake always runs first on all active objects before any OnEnable methods are called. And Unity also respects the hierarchy order, meaning the topmost game object executes first. So, here's what happens step by step. Test1 awake run first, test1 OnEnable, then test2 awake, and finally test2 OnEnable. So, the console output will look like this. In short, Unity first call awake for all objects, then OnEnable for all. Awake sets the things up and OnEnable gets them running. Let's move to the next question. Difference between Time.time, Time.Deltatime and Time.FixedDeltatime in Unity. In Unity, Time.time, Time.Deltatime and Time.FixedDeltatime are used to manage time within your application, but they serve different purpose. Let's break it down. Time.Deltatime gives the total time in seconds since your game started. It's like a running clock that never stops while the game is playing. Time.Deltatime is useful for tracking all our game duration, setting timer or schedule event based on absolute time. On the other hand, Time.Deltatime tells you how long the last frame took to complete. This value varies depending on the frame rate of your application. A lower frame rate results in a large data time and higher frame rate results in a smaller data time. It's primarily used within the update method to make calculation frame rate independent, ensure consistent movement or action regardless of how fast or slow the game is running. As an example, to move an object at a speed of 5 units per second, you would multiply the desired movement by Time.Deltatime. Time.FixedDeltatime represents the fixed time interval in seconds between calls to a FixedUpdate method. This value is constant and does not depend on the frame rate. It can be configured in the project setting. Its default value is 0.02 second, meaning 50 physics updates per second. Physics should be consistent regardless of the frame rate, so Unity uses the fixed data time for fixed update rather than data time. In short, Time.time is a total time since game started, and Time.Deltatime is the time since the last frame, and Time.FixedDeltatime is the time between two physics updates. Mastering these three helps keep your gameplay smooth, consistent and perfectly timed. Let's move to the next question. Can we change the value of Time.FixedDeltatime in Unity? Yes, you can change the value of Time.FixedDeltatime in Unity, and there are two ways to do it. In the Unity editor, yes, you can set it to directly in the project setting. Go to Edit, Project Setting and Time. Here you will find a field called Fixed Time step. This represents the Time.FixedDeltatime. By default, it's 0.02 second, meaning Unity runs 50 physics update per second. If you make it 0.01, the physics will update 100 times per second. But remember, more update means more CPU load, so balance it carefully. This change affects the physics update rate across your entire project. Second way is through script. You can also modify it dynamically while your game is running. Access the Time.FixedDeltatime property and assign a new float value. This can be useful when the switching between modes, like from slow motion gameplay to fast action scene. If you modify it during gameplay, make sure you also handle the Time.timescale for smooth transition. And never change it every frame. Do it only when necessary. So yes, you can absolutely tweak the Time.FixedDeltatime to control your physics update frequency either in the editor or through the script. Just use it wisely to keep your gameplay stable and smooth.
That's wrap for part 4. If this video helped you, hit like button, subscribe and turn on the notification so you don't miss the next parts. And don't forget to drop your own interview question in the comments. I will try to feature them in the next video. If you enjoyed this video and want to support the channel, feel free to buy me a coffee at the link in the description. Thanks for watching and I will see you in the part 5.